Hello, and welcome to Lecture 11, where we're going to cover Section 4.7 from Survey 11th edition, and we're going to discuss the topic of two-body problems. These are force problems that involve two objects and ask us to solve for some quantity about that system of two objects. This section, as you can see, is all about examples. We're going to jump right into the practice. This is a culmination of the ideas we've been introducing, starting with Newton's laws, in particular Newton's second and third law, building on our understanding of the normal force, the tension force, and the friction force, and how to deal with forces that have components. All right, that's what this is all about. Every single one of these two objects solve the system. Some of these problems have many steps to them. They're complex in terms of the space they take up and the number of steps, but they're very procedural and they're all very similar to each other once you find those common patterns of solving techniques. All right, let's get into them. So there are three types of problems we're going to discuss. Type 1, problems that involve two objects applying forces on each other and accelerating in a single dimension. They may include friction, tension, and gravity. All right, so these are 1D two-body problems. Type 2, problems that involve two objects applying forces on each other and accelerating in two dimensions, but at right angles to each other. They may include friction, tension, and gravity. So type 2 are slightly more complex, but we don't have to deal with any components because basically you just have two axes and everything lies along those two axes. Okay, X and Y, right? Type 3, however, are complex problems that involve two objects applying forces on each other and accelerating in two dimensions, like type 2, but where the objects, one or both of the objects, are on tilted surfaces. And just like all the others, they include friction, tension, and gravity, and a combination of those types of forces. Okay, that said, all the forces will include gravity, I guess, except for the first one. So let's take a look at the first one. All right. So example 1. A child pulls on a toy train without friction as shown. They pull with a force of 36 newtons. If each part of the train has the same mass of 5 kilograms, then what is the tension in the connector between the parts? So right here, what is that tension? What is that force? All right, and then if M1 is 5 kilograms, but M2 is heavier, then what is the tension between the parts? How is it different? Is it greater? What to expect? Okay, so let's look at the free body diagram. Every one of these problems is going to start with drawing vectors on the picture, thus making it a free body diagram or a vector diagram, a force diagram, a force vector diagram it could be called. But I always use the term free body diagram. Okay? So let's look at the first step. First step is to write out the sum of forces. By writing F net, that means we're using Newton's second law. I'm going to write F net equals, well, the net forces, and I'll just identify what they are along a particular axis, and then I'll set them equal to MA, and A is along that same axis. In some cases, MA is 0. In other cases, it's non-zero. Okay, so what's happening here? All right, well, I have F net 1 and F net 2. Notice I don't identify the axis they're on because there's only one axis at play here. There's just the x-axis. So I'm assuming they're both along the x-axis. Instead, the subscript 1 and 2 denotes whether I'm talking about car 1 or car 2. So in other words, F net 1 is the net force on car 1, and then net 2 is the net force on car 2. All right, what does it look like? Okay, well, on car 1, it's just going to be 36 newtons minus F connect equals M1A. Okay, for car 2, it's going to be F connect equals M2A. Why is that? Well, let's look at it, right? There's only a single force acting on M2. It's just F connect, and it's acting in the positive x direction, right? Whereas for car 1, there are two forces, the external pulling force and the connecting force between them, the tension between them, but it's acting backwards, right? So that's why it's negative. Now the acceleration I identify as positive because I assume the carts are going to accelerate in the positive x direction. In fact, they have to because there's no force preventing them from. There's no friction here. Okay, so that's our system here. I won't go into that much detail for every one of the examples, but I wanted to kind of start out by explaining the types of steps we're going to see. All right, so how do we go about solving the problem? It's going to always involve algebra because we're always going to have multiple equations. Rarely is the unknown we're looking for just going to show up in a single equation. Instead, the unknown we're looking for is going to show up in multiple equations, and we then have to do some algebra to get that unknown and solve for it. Case in point, this example here, right? The thing we're trying to solve for is F connect, but it shows up in both equations. So does A. We don't know A. That means we have two equations and two unknowns. In mathematics, there's a rule that says as long as you have no more unknowns than the number of your equations, you can solve for those unknowns. Okay? Maybe you've heard of that rule, maybe you haven't. It's fine either way. But the thing here is that since we have two unknowns, acceleration and F-connect, we can solve for both of them. All right? Now here's the thing. We actually don't care about acceleration. I didn't ask for it, so we're just going to not solve for it, although we could have. All right. So a good algebraic technique to solve for our unknown is to add the equations together. So we're going to take fnet1 plus fnet2. That's totally valid as long as we add them together and add everything on the right together and add everything on the left together. All right, so I'd add everything on the right of the equal sign together and then everything on the left of the equal sign together. Okay, when I do that, I get 36 newtons minus F connect, okay, plus F connect equals M1A plus M2A. All right, on the right-hand side, I factor out the A, and then I notice since I have a negative F connect and a positive F connect, they cancel. All right, so then that just gives me that acceleration is just going to be 36 newtons divided by M1 plus M2, or 3.6 meters per second squared. Okay, so why did I bother finding the acceleration? All right, well, I guess maybe I was just wanting to be, thorough in the problem, but honestly, we didn't need it here, although now that I have it, I can then quickly go back and solve for F-connect. That said, I could have done different algebra and just eliminated it, right? So I could have, say, like, solved this second equation for A and then substituted it in. There's more than one way to solve these problems, right? I mean, there's got to be, okay? So then we're going to substitute back into FNet2, and that is in terms of just put the value back in. All right, so if I put the value of acceleration back into FNet2, why did I choose FNet2? Because it's the simpler equation. All right, not that it would be that much more complicated to substitute it back into FNet1. And when I do, then I find that F connect is just going to be M2, 5 kilograms, times A, which we now know is 3.6 meters per second squared, tells me the connecting force between them is 18 newtons. What does that mean? Well, that means that half of the force that is applied is a tension between the two of them. All right, so essentially half the force is pulling the back one, the other half force is pulling the other half of the external force is pulling the front, and they're both accelerating at the same rate. That makes sense because they're equal mass, right? Okay. But what if they're not equal mass? Well, there's just some small differences. I won't start with the same sum of forces. I'm just going to leverage what we already know. So I know that this is going to have the same form, right? Even though they're different masses, it's still going to be external pulling force divided by the sum of the masses. But instead of the sum of masses being 10, it's going to be 14.5 because now M2 is 9.5. It's larger. That means my acceleration is smaller. That makes sense because the total system has more inertia. Thus, the external force should cause less acceleration of the bigger system. Okay? And then I'm going to then plug that 2.48 into FNet2. All right? Now multiplying by 9.5 because now M2 is 9.5. And what do I get? 23.6 newtons. The connecting force between them is 23.6 newtons. All right, M2 pulls on M1 with 23.6 newtons. Likewise, M1 pulls on M2 with 23.6 newtons. Why is this bigger than half of the entire external pulling force? Well, because M2 is bigger than M1, so it gets more than half of the force. All right? Okay, in fact, it should be proportionally more. All right, so there we go. Our first example of a two-body problem. We actually kind of saw these before when we introduced Newton's third law. All right, let's do a similar problem, but with friction. All right, example 2, again, 1D. First thing I start with, draw the free body diagram. I'm going to sound like a bit of a broken record, but this is still going to be a good video where you can go through and kind of refer to techniques if you need to think about how to solve these types of problems. Okay, so with the free body diagram, what forces do we have? Well, we got our one external pushing force. We've got our reaction forces between the blocks, okay? As these like come from Newton's third law. Then we have a friction force acting on the bigger block M and a friction force acting on the smaller block little m. All right, so as I say, this is similar to the last problem, but with friction. The fact we've changed from pushing to pulling, it doesn't really make any big difference at all. As we start with our F net. I'm just going to identify all the forces on big M and all the forces on little m. All right, so on big M, I have the pushing force in the positive x direction based on my coordinate system, minus the reaction force because it points backwards, minus the friction force, and that's going to equal big MA, okay? because I'm assuming they're accelerating in the positive direction. In fact, they have to. They either the friction is so great that there's no acceleration, in which case I'd find the acceleration to be 0, or they move in the positive x direction, because friction isn't a force that can create motion on its own. It can only prevent motion. In other words, it would be impossible for the two blocks to accelerate in the negative x direction. All right? Then we have F net little m has, in terms of, I guess, forward forces, it just says FMM, which is just the reaction force between the blocks in the positive direction. That's this one here. And then it's got the friction force opposing it. That's that force. And then it would be MA. They have the same acceleration because they have to accelerate together. They can't move independent of each other. So they must share the same acceleration, if you were wondering. All right? And then add the two equations together as an algebraic solution technique. I mentioned that before, but here it is in writing. Okay? And so that F net m plus F net little m. All right, what is that going to look like? Well, F minus FMM minus FFM plus FMM minus FFM, right? But some of my m's are little m's, but you see them there. And then adding everything together on the right-hand side, it'd just be big MA and little ma, all right? And then from Newton's third law, I know that F big M little m is equal to F little m big M, all right? Because they have to be. They're equal and opposite forces. They represent a force pair, okay? All right, and then, so they cancel out, in other words, right? Which I had shown before, but just justifying why they do. All right, and then I'm just going to isolate acceleration. I factor it out, right? So we get something like this, okay? And then when I solve for acceleration, it's just everything on the left-hand side, pushing force minus mu k times mg, or mg plus mg, all over the sum of the total masses. Now, this you're going to see so much, so often. You're going to see the sum of masses in the denominator when you solve for acceleration. Almost every system will have some numerator, which will be a complex combination of all the factors, basically the driving forces, the forces that want to accelerate the system, and then all the forces that are trying to impede the acceleration of the system. Okay, and that's what we see here, right? F is trying to accelerate the system. The friction force is trying to stop the system from accelerating. All right, so that's what your numerator will look like, some story like that. But your denominator will always just be the total inertia, just the sum of the masses, every time you're solving for acceleration. And often that's what I'm asking for in the problem. So I'm kind of trying to be consistent. Everything else we could solve for the tension, we could solve for any unknown of the system, but often it's the acceleration kind of makes sense because that realistically can be the thing you might be trying to test and compare, right? You can measure everything else, the masses that is, and the angles, but you might want to then predict what the acceleration is because that's harder to measure, isn't it? All right, so anyway, let's plug in our values. All right, so there's our pushing force, there's our friction coefficient, mass times gravity, and then one thing I've done here is I just have the total mass times gravity. So big M plus little m together is 1.23 because it's 1 kilogram plus 230 grams. And the same thing in the numerator, I just added the masses together to write 1.23. When I do that all, I get a number, and it's 3.51 meters per second squared. All right? Great. Got the acceleration of the system. All right? Now, what about the reaction force between them? Well, that's pretty easy. I just go back to the simplest one to do that, which would be F net little m, right? Because there's less going on in that equation. And then I'm just going to isolate the reaction force between them, F sub little m big M, right? This force right here. All right, and then factor out the common value of m, because this friction force, by definition, is just going to be mu k little mg, which I've done, right? And then, which I've written here. Factor out the m, because there's an m in both terms. All right, plug in my values, because little m is 230 grams, friction coefficient, gravity, and then the acceleration I solved for in part A, right? Because I needed that acceleration. All right, and there we go, 1.45 newtons. That's the force between the blocks, all right? So it's actually a pretty small portion of the overall force. And that's because the leading block is M, little m, right? If the leading block was big M, we would have a different reaction force between them, right? So it's really interesting how this works out, how the idea of the reaction forces work, okay? But we just follow the evidence. We just follow the algebra, starting with a good, thorough free body diagram. All right, but we got a few more to do, so let's move on. Okay, so example, oh, shoot, my naming is off. I didn't realize that. Oh, that's too bad. Here we have example 3, but I mislabeled example 2. I won't worry about it. All right. So this is something called an Atwood's machine. All right. I want to acknowledge the name because this is such a common type of physics problem. The Atwood's machine. It's not really so much a machine. It's just a device that has two masses that are free to move over some pulley, and then one of them is always heavier than the other, so it accelerates in the direction of the heavier one. All right. So let's solve this problem. Right. It's just going to be same sort of thing. Sum of forces, find the acceleration, because that is what I asked for. I asked for the magnitude of the acceleration of both weights. Okay, so here's my free body diagram. I'm acknowledging there's the tension force acting on both blocks, and there's a gravitational force acting on both blocks that is unique to their mass. Okay, I'm defining positive y as upwards. Now, interestingly, I'm defining positive y as upwards for both blocks. Now, that might not seem interesting at all. We just did that in the previous example, defined positive x as to the right for both blocks. All right. There's actually something pretty significant there. I'm going to mention it and come back to it in a minute. All right, so here is our sum of forces on blocks 1 and 2. Again, I don't specify the axis because there's really only one axis to consider. All right, for 1, there's the tension pointing up minus gravity pointing down, and then there's M1A. All right, so that's the acceleration of block M1, okay? And, well, A is at least. And then for block 2, there's tension pointing up, gravity pointing down, and then negative M2A. Why negative? Well, because I know M2 has to accelerate down, okay? If M1 goes up, M2 must go down. M2 is the heavier one. M1 is the lighter one. I would have had to look at that ahead of time to acknowledge that M1 must go up and M2 must go down. Why must they? Because there's no friction. There's nothing else in this system, okay? And we know that Ft, the tension force, is shared by both blocks because both the string and the pulley, okay, are massless. Now, I mentioned before that strings will always be massless in this class. Massless pulleys will not always be the case. We have a whole chapter essentially where we'll deal with pulleys with mass, because then we have to deal with their inertia, okay? And that's totally solvable, unlike the roping a complex problem that will require calculus. We can deal with a single pulley that has its own inertia. It's just a little bit different because it's rotational inertia, but that's a story that we'll dedicate a whole chapter to down the road, okay? But point being still, getting back to the problem, we got a sum of forces, okay? And we have a negative. We have a negative because we acknowledge that M2 must go down. The acknowledging that negative isn't very different from acknowledging that the gravitational force points down, okay? Now, we're going to subtract Fnet2 from Fnet1, okay? See, I left that off. I should say Fnet1. All right, so then when we have Fnet1 minus Fnet2, all right, yep, all right, so there you see it, Fnet1 minus Fnet2, all right, so then Fnet1, that's this here, on the left-hand side, there it is, all right, and then this is, there it is here, okay, and then we're going to subtract Fnet2, all right, and this is, so we'll subtract the friction, and then if I'm subtracting this term, well, I'm going to distribute the negative so it becomes positive, and gravitational force on block 2 is just M2G. All right. Notice then when I do this, the tensions cancel. That was the point because I'm trying to get rid of the tension. I could solve for it, but since I wasn't asked for it, I'm just eliminating it through this particular algebraic technique. All right. And then since I am subtracting F2, then I'm going to have minus a negative, right? So then this will become a positive as well. All right. So then when I clean things up a bit, I have on the right-hand side, I just have A times M2 plus M1. And on the left-hand side, I just have G, right, because I just have these two terms, times M2 minus M1. Go ahead and solve for A. And look, we get this really kind of neat, elegant result. The numerator is just the difference between the masses, and the denominator is the sum of the masses. That is the beauty of Atwood's machines and their popularity with, physics teachers. Because for simple Atwood's machines with no friction, no mass in the pulley, this is the result of the acceleration. All right. So then in this system, we just plug in what we got. I left off G there. I'll have to go back and fix this when I upload it, because you can see here the G is there, and then I just left it off. I do put it back here numerically, so the number is correct, but I did forget to write the G. All right. So please excuse that. All right. And then we plug in the numbers, and we find out the acceleration is 4.13. It will always be less than gravity, because if you think about it, if you make M1 0, right? If you just make this one massless, what happens, right? Well, then it just becomes M2 over M2. Remember, there is a G in front after all. So this is G times 1. Well, that's just free fall. That would just be M2 in free fall, right, if M1 was gone. So that's the biggest it could possibly be. As M1 becomes much, much smaller than M2, we get closer and closer to free fall, or closer and closer to an acceleration of M2 downwards of 9.8. But in this case, it's not at all, right? It's 4.13, because M1 is pretty substantial, right? It's about half the weight of M2. Okay, now, again, we had to acknowledge the direction of acceleration because we chose a single coordinate system for both blocks. And if one block went up, the other one had to go down. Keep that in mind. Again, I will mention that in just a moment. All right, so example 3. Now we're on to a different type of problem. These are ones that aren't 1D, they're 2D, but they're at right angles, so they're still relatively simple. All right, one block with mass 5.5 kilograms rests on a flat table and is attached via a massive string and pulley to a hanging block of m equals 6.7. All right, so big idea, same idea, big M and little m. All right, in terms of notation. What static friction coefficient is needed between the block and the table in order for the system to remain at rest? So this is going to be one we haven't seen so far. This is where everything's just going to be equal to 0. There is no A. Okay, so instead we are solving for something else. We're actually solving for the static friction coefficient. Okay, but same idea. We draw a free body diagram. Notice that I have defined a coordinate system here. I defined positive y as downwards for this block and positive x as to the right for that block. Now, I'm saying that this coordinate system is shared by both of them essentially, the way I'm drawing it, but really I'm only going to use y for block 2, and I'm only going to use x for block 1, all right? So here we have f net 1x and f net 2y, all right? What are the forces? Well, we've got the tension force and the friction force acting in the x direction on block 1, which is block big M, okay? And then we have on block 2, which is block little m, we have gravitational force in the positive direction, because again, positive y is downwards, minus tension, also equal to 0 because everything is going to remain at rest. Okay? Then moving right on, and we also know that the friction force is equal to mu SFN, which is just equal to mu kmg because level ground, so no need for F net 1y. Okay? I'm just saying we don't need that net force equation because we're familiar with this idea. It's the simplest case of friction. It's just level ground, okay? All right, so then I'm going to go back to F net 2y and write friction as just mg, because that's what it is, right? Friction is just equal to mg. And again, this only works because the system is not accelerating. Otherwise, it would not be equal to mg. All right, and now finally go back to the first equation, the first net force equation, F net 1. Then I have that the tension, mg, is equal to FF, the friction, which is just mu s big mg, g cancels, and then my friction coefficient then is just a little m over big M. Wow. Well, first of all, we expect it to be dimensionless, so it should be a ratio of something. In this case, it's a ratio of masses, all right? Now, technically, it was a ratio of forces, but the gravity canceled out. That's why it looks like a ratio of masses, okay? And so it's just 6.7 over 5.5, which is 1.22. That's fairly unrealistically large. That's possible, but most static friction forces are smaller than that. And again, it is possible for static friction forces to be a little bigger than 1, but most things aren't that sticky. They aren't that rough. All right? So we probably would want some other force to keep the system at rest and not just rely on friction because that's a lot of friction necessary. All right. So now it's a variation on theme here. Let's look at the same type of problem, okay? But now there's kinetic friction and the system is accelerating. So instead of the system remaining at rest, the system is moving. In other words, block little m is big enough to pull the system. Big M can't stop it. There's not enough friction in this case. So now instead of using static friction, I'm using kinetic friction. And that means that instead of both the F net equations being equal to 0, they're going to be equal instead to an acceleration. Okay, well, a mass times an acceleration. Okay, so do a free body diagram again. Okay, this time I'm more explicitly showing the forces in the y direction on block, block big M, all right? Also, I've defined a different coordinate system because I can, all right? I'm defining positive y as upwards, kind of a more traditional coordinate system, all right? Now I am going to consider all 3 of the net forces, F net y for big M, F net y for little m, and F net x, okay? F net x would have to be for big M because little m is not moving in the y direction. So I just left the subscript off. All right, what's happening in those 3 directions? All right, well, a lot of the similar stuff, right? In the y direction for big M, there is no acceleration because big M is not moving up and down. It's only moving left and right. It's only going to accelerate that way, right? So that's the one case that's 0. Meanwhile, F net y little m is tension pointing up this time because I defined positive y as up, minus gravitational force, mg, and that's going to be equal to negative ma. Why negative? Because I know that little m must accelerate down. Meanwhile, for the net force in the next direction, tension minus friction equals to big ma, because I know m must accelerate in the a direction. And again, this negative comes from the fact I'm using the same coordinate system for both blocks. Okay? Then I rewrite some things that are simple. For example, I just write that the normal force is equal to mg. This is honestly the step I skipped above, but here we see how we can do it more explicitly, right? Level ground, simple case for normal force. Then we also can figure out that the tension force from our hanging block is going to be equal not to mg this time, but to m times g minus a. So in other words, the faster the system moves, the less tension there is in it. That makes sense, right? Because if say, for example, little m was really, really big, then the system would be accelerating, at a rate that approaches a free fall acceleration for m, and that means that the tension would be approaching 0, right? So the faster it accelerates, the less tension, okay? And then I'm going to substitute in this tension into this final equation, F net x. So tension gets replaced by mass times g minus a. Friction gets defined as mu k mg. It's negative because it points in the negative x direction. And then I have just big ma, all right? And then I'm just going to do some algebra here, right? Put all my a terms on one side, all right? So I distribute this m, okay? And then put all my a terms together. I put them on the left-hand side. And then everything that didn't have an a on it, I put on the right-hand side, which involved taking an mg, all right? And actually, I just swapped the sides. So I kept the same signs that you see here, but just wrote everything with a on the left, okay? But you can check that algebra for yourself. And here I have the acceleration, okay? Now, the g is correctly put in there. Where did I forget the g? I forgot the g on the Atwood's machine, right? It should be there. That's too bad, too, because the Atwood's machine, such an important example. But I bring that up on the Atwood's machine, not to go off on a tangent, because this looks an awful lot like the Atwood's machine, doesn't it? It's got total mass in the denominator, and in the numerator, it's got difference between masses. Well, almost, right? It's got the difference between the driving mass, the mass that wants to accelerate the system, and the inertia that wants to slow the system down, which isn't just the mass of m, but in fact the mass of m times some friction coefficient, all right? And if the friction wasn't there, then what would happen? Well, then we would just have just m in the numerator. If there was 0 friction, then it would just be m over the total mass, okay? Because then the only thing slowing the system down would be essentially the inertia of the system, okay? But since friction is there, it slows down even more. All right, and let's plug in our numbers, right? I've just rewritten it as a single line, more like how you'd enter it in a calculator. And we get 6.02 meters per second squared. So pretty fast because little m is a pretty big mass, all right? So it's able to accelerate the system quite a bit. Okay, all right, so you see, doing the same process, okay? Now let's do it with two-body problems where there's a tilt, an angle, all right? So I originally I put this font in blue. It should have been in purple, so you can see I changed it in purple after the fact. All right, so let's go through these ones. At pretty soon at a point, I'm going to start really kind of glossing over the really big final two examples, but I do want to spend a minute on at least one or both of these ones. Okay, so example 5, all right, which should be example 6. The system shown below consists of two blocks of masses m1 and m2. Block 1 rests on a frictionless incline of angle alpha equals 26.9 degrees above the horizontal. What is the magnitude and direction of the acceleration of both blocks? So we're just solving for the acceleration. We're given all the information as in previous problems, similar information, but we have a tilt now. So what does our free body diagram look like? Well, here we got the forces on block 2, and here we have the forces on block 1. No friction. That keeps the system a little bit simpler. But we choose a coordinate system where, right here, this gravitational force has components, all right? But it has components relative to y, not this y, but its own y, right? Y, I guess would be this direction, okay? And I didn't draw it in the figure because it doesn't come up much in the problem. But notice what I've done with the coordinate system here. I've defined separate coordinates for block M1 and block M2. I'm going to mention that again because I think it's even more prominently displayed in the next problem, or maybe it's the one after that. But this is interesting because in doing that, I don't have to make any assumptions about the acceleration. For example, I don't have to assume that m2 is going to be big enough to accelerate downwards, because m1 might be big enough to actually accelerate downwards. If m1 is, say like 5 times heavier than m2, then certainly it's going to pull the whole system. m1 is going to slide down the incline at an angle, and m1 will go or m2 will go straight up. Well, that's the thing. Since I don't want to make an assumption because I'm not sure, it's not easy to tell, unlike with Atwood's machine. It's not necessarily easy to tell, especially once you introduce friction. It's not easy to tell which direction it's going to go in at first pass. Then don't force yourself to make an assumption. Instead, choose separate coordinate systems for both blocks. That way you can define both accelerations as positive, and if the accelerations come out as negative, then you know that the accelerations are in the opposite direction that you guessed. Let me say that again, okay? Since I'm defining positive x as up the incline and positive y as down, I'm assuming that the system is going to accelerate with m1 moving up and m2 moving down. Okay, I'm assuming that the hanging block is massive enough, and that's the more likely case, that it's going to pull m1 up the incline and it's going to move down. Okay, but again, I'm just going to solve for a, right, with those two separate systems. I'm not using the same coordinate system for both of them. Now, if I find an a that is positive, that means that my assumption of positive directions is correct. But if I solve for a and it ends up being a negative value, that means that actually m2 is moving in the negative y direction and m1 is moving in the negative x direction. My assumption of motion was wrong. But it's great because it just worked out. It just comes up in the final answer. All right? Now, does that mean you should always have separate coordinate systems for problems? It depends. So I guess no, right? For the Atwood's machine, it's so straightforward that it makes sense just to use positive y as up for both of them. Okay? It's like it just naturally flows that way. But I make a big deal about this because that can be a real sticking point. Signs can be a real sticking point, right? Getting a negative wrong is incredibly easy, right? And you're only going to not get it wrong, honestly, with practice and kind of checking your work. But thinking about what it means to have separate coordinate systems, what it means to not have separate coordinate systems is a good starting point. And I want to at least get that idea in your heads to begin with. All right, but anyway, now we can move on with the sum of forces, the F net equations. F net x and F naught y. Just two of them, right? Because they don't have to really worry about friction here, so I can keep it pretty simple. All right, in the x direction, which is this is really the only axis that I'm really going to care about for block 1, right? In fact, absolutely the only one I'm going to care about for block 1. And then in the y direction, I should say for block 2, I'm only going to care about the y direction, right? So anyway, so the F net x is just tension minus a component of gravity, okay? So it's just this component of gravity. So I drew a y component of gravity, but that doesn't come up in the problem. It's just because I wanted to use the same free body diagram that I'm going to use for the next example below. So this is not relevant. The only component of gravity I care about is Fg1x, all right? And Fg1x is m1g sine of alpha. Why is it sine of alpha? Because alpha is this angle right there. By geometry, I know that this angle is alpha, and so must that angle be alpha. All right, and then sine because it's the opposite side from my angle alpha. Okay, all right, and it's negative because it points in the negative x direction based on my coordinate system, and here is my assumed direction of positive acceleration. All right, same sort of thing for y. Gravity points down because my choice. Friction points in the negative direction, up. Okay, positive for gravity, negative friction, and then positive acceleration. All right, let's do the algebra. I'm just going to add them together. That's what I'm showing here. Okay, when I add them together, I get this. Tensions are going to cancel. All right, solve for A. All right, when I solve for A, I get a really similar expression, right? G in the front, driving mass leading the numerator, subtracting the mass that wants to slow the system down, and then the total inertia in the denominator. All right, plug in my numbers, and there we go. Notice how this looks really similar to the one we did before, whereas m2 minus mu k m1. Here, instead of the mu, because there is no friction, it's m1 sine alpha. Right? So the thing that's slowing it down is just a component of its weight, honestly. And it's weight because I could distribute the gravity, even though it looks like mass here, right? But you have to imagine distributing g. All right, plug in the numbers, and there we go. 2.57, and it's positive, which means my assumption that positive x is going to be the direction of acceleration and positive y is going to be the direction of acceleration was correct. All right, M2 is indeed big enough to pull the system down. All right, let's do it again. Same problem, but this time with friction. All right, here you can really clearly see that I have a full-on coordinate system for block 1 with an x1 and a y1, and then a whole different y. I don't even bother calling it y2. I just call it y without a subscript for block 2. All right, so totally separate coordinate systems for both. How is that allowed? Well, I just have to make sure that, that they're connected to each other in some physical way. What's the physical way they're connected? The tension, right? The tensions are equal to each other. All right. So let's set up our sum of forces. This time we'll have 3. Why is it more important to have 3 in this one? Because we introduce friction. Because we introduce friction, now this component of gravity is going to matter, because this component of gravity is going to set the magnitude of the normal force. The magnitude of the normal force is going to set the magnitude of the friction force, which means the friction force is going to show up in the axis of acceleration. That's why it matters. All right? So 3 sums of forces, 3 net forces. All right? Very similar type of thing, right? We've got tension minus component of gravity, now also minus friction, and this is in the x1 direction. In the y1 direction is just normal force minus the component of gravity. Essentially, we're only going to be using this equation for one purpose alone, and that's to solve for Fn, that's so that we can substitute it back into friction, right? In the y direction, just like it was above, all right? We're going to use the definition of friction as mu k Fn, right? And then use the fact that Fn is equal to m1g cosine alpha, because it's this side of the triangle, all right? To find out that the friction force is mu k m1g cosine alpha. All right, then F net x1 becomes this, okay? And I'm moving at a good clip here because this is all the same ideas, right? And you can kind of follow along, and I think I don't want to repeat myself too much. Okay. So anyway, continuing moving at a good clip, and by adding F net x1 and F net y2, again that's the same sort of algebraic trick. I just wanted to make sure I did some work to set them up, so when I added them together, things canceled nicely. I do this. This cancels out the tension. All right. I'm left with more terms this time because friction did complicate things. But you can tell that as I solve for acceleration, I'm going to get the total mass in the denominator again. And here we go. There is our symbolic form of our acceleration, and then we can plug in the numbers down here. All right. But taking a quick look at the symbolic form, what's different than when there wasn't friction? Well, we're just subtracting by more. Before we were just subtracting by a component of gravity. Here we're subtracting by a component of gravity as well as some friction. All right. So we're adding the friction effect to things. Okay. And let's see. Oh, I want to check something here. So when I factored out the negative m1, I keep doing this sort of thing, and I'll notice in the video. So I apologize for anything that makes it confusing, but maybe you see how this can happen, and it's good to check your work. So when I factored out the negative m1, because notice this negative m1, I was moving a little fast, and I forgot that means that this term, after I factored out, should be positive. And the reason that I notice right now it should be positive is because if I leave it as negative, that's actually telling me that introducing friction somehow is speeding the system up. Well, that's impossible. Introducing friction has to slow the system down. In other words, I'm subtracting by a total bigger number. So there must be a positive there. So this should be plus. And I didn't do that in the calculation. So this number is too big. It will be a little bit smaller because this should be a plus. I'll fix that in the notes and re-upload them. Okay? And so this is the wrong number. I'm guessing it's probably like 3.5 or something. Okay? Okay, all right. Well, I got a couple that I have checked the answers on. Let's move forward. All right, so these are the last two. These are ones where it's tilted on both sides. Okay, so again, I'm just going to kind of hit some high points on these ones and move on. This one we have, so it's very much like example 5, where there's no friction, but both blocks are on tilts and they're on their own unique angles. What does the free body diagram look like? This. You might think, oh, it's really ugly, but it's got all the same ideas. It's got a tension, all right? It's got a normal force. It's got gravity, of which we're taking components, but it just has those for both blocks, okay? We have a coordinate system for block A that's tilted, and we have a coordinate system for block B that's tilted appropriately to the two different tilts, all right? And all I'm going to do then is say, oh, okay, if acceleration is positive, then it's going to be moving in the positive XA direction and the positive XB direction. And that's actually pretty important because notice here that I define positive XA as up the slope and positive XB is down the slope. And the reason I say that's important is because I don't want them to disagree. I don't want positive xb to be defined as up the slope, because then I'm going to get a negative for one of them and a positive for the other. And that's going to be really hard to interpret what happened. So I want my positive directions to agree for the two blocks. Notice I've carefully done that every time I've used two coordinate systems. Positive agreed. Positive agreed. So if the system is moving one way, then it's going to be positive in all of the coordinate systems. All right? If the system is moving the opposite way, so if the system is moving this way instead, then it's going to be negative for both my chosen coordinate systems. Make sure you do that when you draw your free body diagram. All right, but other than that, it's a lot of the same steps. Set up a sum of forces, okay? There's going to be F net XA and F net YA. Likewise, there's going to be F net XB and F net YB. So we have a full 4 F net equations. We've only seen up to 3 before. This is 4. Why 4? Because it's tilted on both sides. Okay, now what I should highlight what we're solving for, just acceleration. Okay, again, I think the most natural thing to solve for. I just want to introduce kind of the idea of these problems. I could ask you for anything. There's 100 variations on these problems, but the basic idea is you always set up your free body diagram, write the sum of forces. All right. So let's think. Okay, well, acceleration is going to show up here. My 2 y equations are going to be helpful for finding what? The normal forces. Why do I want to find the normal forces? Well, actually, in this case, I don't really care that much because there's no friction. So actually, to be honest, I'm not going to use these equations that much. I wrote them down because this is kind of a flexible version of a setup that could be used if there was friction, which I'll show in just a minute. But here, these aren't going to be that helpful. Right? So my main focus are going to be on the blue equation and the green equation, which is why I've colored them. All right, so moving on. All right, and from the green equation, we get the value of tension. All right, and then we're going to substitute that into the blue equation. All right, so now we've eliminated tension. So now we have an expression that just has a single unknown a, because we know everything else. We know m, we know g, and we know theta 1, and we know theta 2. All right, so then I'm just going to isolate a. All right, there we go. All right, total mass in the denominator. And then up top, we can see that the value that's driving the system and then the part that's slowing it down. All right, let's see if our a is positive. It is. All right. So my assumption that block B is going to go this way and block A is going to go that way was correct. And why would I have guessed that? Well, if I look at it, B is a little bit heavier, and I think the slope is steeper. So theta 2 is 62. Well, yeah, whereas theta 1 is only 26.4, so it's not drawn the scale. That means that theta 2 is significantly steeper and block B is a little bit heavier. That basically tells me, since there's no friction, that B is going to be big enough to pull everything in that direction, in essentially the counterclockwise direction. Okay? So it was a good assumption then on our acceleration. It is going that way, and our magnitude of acceleration is 2.55 meters per second squared. All right, let's look at the last one. All right, this one has everything. It's a whole kit and caboodle. All right, this is a problem with 2 separate slopes, 51 and 21 degrees, and friction. Okay, here's the free body diagram. All right, there's a lot going on because we've got friction. All right, we've got normal force, we've got gravity with its components. Okay, and then we've got MB moving in this direction. Okay, if it's moving in this direction, that means that friction is actually going to point uphill. All right, now that's a big one right there, because you have to make an assumption about the direction it's moving. When friction is at play, you have to realize that friction opposes motion. So friction can't point this way if MB is moving in the direction that V is showing. Okay, now here's the thing. Let's solve for the acceleration of the system. All right, if I solve for the acceleration of the system, then what value am I going to get? All right, well, let's see. So the net force for each block, set it up. I'm going to have 4 net force equations. All right, definition of friction on a little side note here. All right, here they are. All right, and then we're just going to continue with the algebra. All right, so with F net Y finished in use, since we have the friction force for both blocks, we can rewrite F net X for both blocks. All right, so again, just doing some rewriting in algebra. All right, now we have 2 equations and only 2 unknowns. All right, and then we'll eliminate tension and just solve for A because that's what we were asked to find. All right, and then we go ahead and solve for acceleration and we get negative 2.54. Well, what does that mean? That tells us that our assumption that block B is actually going to go downhill is wrong. Now again, I use this figure that already had the V put into it, but I do make sure this is to state this is an assumed velocity. Well, it turns out it was wrong turns out that actually what's happening is the system is going to go the opposite way, okay? So that negative tells you that your assumed direction was wrong. And to some extent, it actually tells you you have to then change the direction of friction and then solve for the correct acceleration. But it's a good starting point, all right? All right, so I hope this, all these examples, kind of seeing all this practice of free body diagrams, specifically for two-body problems, has really shown you what force diagrams are all about and the systematic way to solve problems like this. Well, anyway, thank you so much for watching, and I will talk to you all soon.